welcome to another fibre laser learning lab. We focused last time on the lens, no pun intended, because the lens is actually the most important part of this machine. Yeah, I know that without the fibre laser itself it wouldn't work, but equally well you wouldn't be able to do anything with this machine without the ability to amplify the power through the lens. So last time we checked out the focus on this machine, and we now understand that we can, if necessary, use the focus as a mechanism for controlling the softness of the heat that we put down onto the surface. It's just one of the many parameters that we can play with to try and do this. Now that's quite an important factor for today's session, because what we're going to do today is something that I know can be done because I've heard and seen of other people doing it, but I've got no idea how it's done. Maybe they don't either. As an engineer, I know quite a lot about some of the material processing that you have to do to get materials up to their finished state. Now, something I don't have much in the way of to play with is clear anodized material, because that's today's challenge. We're going to try and find out if we can black mark clear anodized aluminium. Now, technically, when you think about it, there's nothing in there to cause it to go black. We've got an aluminium substructure there with a very thin layer of aluminium oxide sitting on the surface, which has been created by an electrolytic process, and then the microgranular structure which has been created by that process is then infilled by a sealant. We have to look at the question and say, well, what is that sealant? Because whatever that sealant is must be the thing that's allowing us to make the mark black. So I did a little bit of research, and it turns out that the sealing material that's used for anodize is usually based on something called a nickel acetate formula. We need to understand how to control the machine itself, but the fundamental problems that we're going to encounter are all to do with materials. And this is the first example. We've got to understand what and how this material reacts to light, so that we can apply the right sort of pulses to the surface to create what we're after. Now, the fact that it is a surface process means that probably we haven't got to break through. So we're not going to be using powerful pulses to pierce through the surface. We're somehow trying to get very accurate heating to the surface to modify the chemical there in some way. So let's just have a look a little bit further into the chemistry of what's going on. So we know that it was nickel acetate that was used there to create that final sealing process. And here we've got the data sheet for nickel acetate. And when I look further into the chemistry of nickel acetate, toxic gases and vapours such as nickel carbonyl may be released. When nickel acetate is heated, it loses its water of crystallization and then decomposes to form nickel oxide. Okay, so we've now got to go hunting further. What's nickel oxide? Nickel monoxide is a green to black coloured inorganic compound that then turns yellow and produces toxic gases upon heating. So now we've got to decide the best parameters on this machine to create a very soft heating effect. The point I'm really making it, I could spend ages chasing around parameters, but now what we've done, we've narrowed down two things. Number one, it's a chemical process, and number two, it doesn't require a great deal of heat, so we can now try soft heating. Okay, so here's almost my total stock of anodized aluminium. It's a piece of angle which I've cut back into flats so they're easy to work with, and a piece of anodized aluminium tube. Now, from what I've seen, there's mainly only surface marking, not depth cutting into the material. So looking at my power matrix chart here, I would suggest that we're not going to start off down here. Look, we've got lots of burning down here. That means that although we've got a lot of range of pulse power across the top here that we could play with, all of them down here at these low frequencies are very heavy burning. What we need to do is go up the frequency scale and I know peak power is supposed to be at 850, I think, if my memory serves me right. 2 milliseconds, 2 nanoseconds, 850 is peak power. Why not use what numbers I've got here, which is 1000 and 2 nanoseconds. So I think we'll start off with that. This is 500 millimeters a second. Well, we could start off at that. I don't have a great deal of material to play with, but what we'll do, we'll draw a little square which is 4 millimeters square. I will just put a fill in that, line spacing to 0.03. That's basically half the width of the spot, so we should get a 50% overlap on every spot. We've got the loop count to 1. Speed, let's try the 500 because we know that that's roughly in the right sort of ballpark. Power 100%, frequency 1000 kilohertz, and pulse width 2. Okay, so 6.15, not 6.25. So let me set the part height down here, 6.15. Okay. Very dark grey as opposed to black. Maybe we'll slow it down a little bit, give it a little bit more time to heat up. Now here's where my little chart comes in handy, because we're running this at 500 millimeters a second. So that means I'm producing 1700 pulses or 1700 dots per millimeter. Now if I change the speed to 200 or 250, look, I can go from 1700 dots per millimeter to 4250 dots per millimeter. So the heating effect will be greater if I run at 200 millimeters a second. Now I'm going to note down all the data for this because I don't want to lose this valuable data. To be fair, there probably looks to be no difference in the density of that black. In this light it could be construed as grey. It's actually not bad. It's a pretty good matte black. If I feel it with my fingernail, there is just a small amount of depression in that cut. Well, I did say that the material that we're trying to blacken goes down into the material. Maybe that counts for why we've got a very slightly grey look. So we'll now be a little bit brutal and we will reduce the power to 50%. Well, the fingernail test tells me that we've got very little depression on the surface now. I could definitely feel something there, but I can't feel it here. So let's see how low we can go with the power. Okay, so we're now going to run this one at 20% power. I think we're more or less on the surface. Well, it might be considered running before we can walk, but hey, I'm going to try scanning across a piece of tube. We're looking at 23.3. 23.3, which is the maximum height, and as it goes over the edge there, it's going to drop off. So that's actually going to test the focal accuracy of this process as well. As we established in the previous session, focus has got a very large range on it, so we shouldn't actually notice any effect at all as we go round this surface. The focus is correct on the edge of the mark, and it's going to drop away by maybe 1 millimeter. This does another check as well. First of all, we've got a different anodizing, or we've got anodizing on a different type of material. It shouldn't make any difference, but hey, let's see what we get. It's definitely a different material. Instead of black, we've got white. No, this is not the f-theta lens off the machine. This is a macro lens I'm going to plug onto the front of this camera in the hope that you might be able to get some idea of what I'm seeing under the microscope. Now, I've managed to put this into some bright sunlight, and the sunlight is over to the right hand side of the camera. And I think you'll be able to see, by virtue of the small shadows on the left-hand side, how raised up this surface is and how, relatively speaking, how rough it is. So the first question is, how do we reduce the surface temperature? We've already got the power turned down to 20%. We could go the other extreme and we'll go right from 200 millimeters a second up to 1000 millimeters a second. Let's try that, because that means that we should be getting a lot less power, 5 times less power per unit area. Now the one on the right is the second one that's done at 1000 millimeters a second. And it does appear to be a slightly smoother finish, and to be fair, it does look to be slightly darker in this bright sunlight. But when I look at it with the naked eye, there really isn't any difference. So we've almost only got to turn the machine on and pick some lottery numbers, and hey, we're going to make this material white. Knowing that I'm working on black marking of anodized aluminium, Lotus Laser have been very helpful this morning, and they sent me across their parameters for the black marking that they use. Let's have a quick look. Loop 1, speed 400, power 42%, that's a bit exact, frequency 825, pulse width 2, so they're more or less using maximum power pulse like I am, so their parameters are not far off those that I was using for the first samples. We'll try it on the tube first because I'm already set up for the correct focus height. So we'll delete the Lotus Laser logo and we'll just work with this little Q code. After all my failures on this material, let's see how the Lotus Mark program works. Took about 3 minutes 45 because I was a little bit slow on the stopwatch. Right at the edge, where it's gone out of focus, we've got colour. So what I'm going to do now is to actually lift the focus up to see if we can bring that out of focus onto the top here to make it darker. A millimetre? Let's try a millimetre. We're definitely getting colour now in one or two places, look. So I'll increase the focus a bit more, we'll go up another millimetre. Well, there's the Lotus Laser mark, and as I start moving along here, that's my last mark. Right, we're going to try those same settings right down the centre now. There's definitely something different about that because I can feel there's some depth in it. We're now back to the Lotus Laser Q code settings. Well, apart from taking a long time, none of those work. We've now raised the focus height up to 27 from its nominal 23.8. And these are the Lotus Laser settings. You can see we've got a lot less power there now because we're using a lower part of the beam. Now, I'm definitely not cutting into the surface. and that looks pretty black whichever way I catch it in the light. So let's go back to my settings now. Well, it's there again, it doesn't disappear. I think I've put more power into that. Well, that's looking more promising. But is it cut into the surface? The answer is no. So we've managed to get colour 5 times the speed that the Lotus Laser setting was. So we've now changed the line spacing to 0.01. And we've still got some quite nice text. So most of that control was gained through messing around with the focus and softening off the power. I found some more silver anodized aluminium from a job that I do for somebody else. I have these as a surplus product. Now, I've already done a little bit of experimentation because this is boring watching all this stuff. If we catch this in the right light, we've got black marks for some of them. And as we turn it around, some of them go black and some of them go and disappear. So they are light sensitive. This one at the bottom here was the first one that I did. In fact, it was that way up. And that is the Lotus Laser standard black marking. It's pretty good. But then again, that one there is the Lotus Laser standard black marking, and it's absolute rubbish. And the only difference is the position that I'm at on the material. As you can see, some of these, if we take a look here, this has got a little black spot right on this corner, but everywhere else it's pretty dull and grey. So from that I have to conclude that there's a varying thickness across this surface in the anodizing. That's what we were finding with this product. Although it was anodized, it was very, very thin anodizing. The thicker the anodizing, the deeper these pores, and the further into the material we can engrave and still hit this nickel acetate. That certainly appears to be proving by these tests. You know, I'm now going to check what the anodizing is like on this outside surface here. So if you catch them in the right light, the difference between 1 and 3 isn't all that great. But 1 takes 3 minutes 45 and 2 and 3 take about 15 seconds. Now, that works on this surface, but of course it was pretty rubbish on the bottom surface. I mean, this was the Lotus Laser mark on the bottom surface, and it's lovely and black. So I'm not arguing with that as a set of settings. All I'm saying is it depends on the quality and the depth of the anodizing, what you can actually do with it. Now you can clearly see the difference there now, look. I mean, those marks hardly show at all. But the Lotus Laser mark settings, slow as it is durable no matter which way I fire the light at it. I mean, here we can clearly see that it makes little or no difference as to which one of these. That one is too weak, but these here were equally as good as this one, which is the Lotus Laser mark. But we've also seen that if we can get a fairly thick layer of anodizing, then the nickel acetate penetrates into the surface deeply, and even if we engrave away a small amount of the surface, we still get this lovely black marking. And we do this in something like about 15 or 20 seconds, whereas this one, as I said, is taking something like nearly about 3 3/4 minutes. Well, I think we'll just have a quick 20-minute sum up of what we've seen today. Sorry, I'm joking. Very quickly, I think we've established that there is no one magic formula that gives us the opportunity to black mark on clear anodized aluminium. We've established what the mechanism is, and it's a chemical mechanism of converting nickel acetate into nickel oxide, and it only happens on the surface or to a depth that the nickel oxide can penetrate into the surface of the anodized material. But what we've established is the region in which you're going to have to work. Very, very short pulses, may be backed off with something like about 60 or 70% power, and speed is not that important, but but I've been using speeds of around about 200 or 300 millimeters a second. But the most important thing and difference between my settings and those of Lotus Laser are that Lotus Laser were using 1 micron line spacing and I've been using 30 micron line spacing. So by default, my speed is going to be substantially greater than their speed. Hence I can get to 15 seconds for one of those Q codes. With the right material that I'm going to use for my product, I might even be able to get it down to 10 or even 5 seconds. It really depends on the quality and thickness of the anodized aluminium that you're using. Okay, so it took 4 minutes, not 20 minutes. Until the next time, cheerio. Well, I think you better settle down for another few minutes because I've got a little bit of footnote to add to this video. Now, a couple of days ago, I went to visit the guy that does my anodizing. And I had a word with him about the chemicals he used for finishing off his product, for sealing the anodize. I asked him if he used nickel acetate. Oh no, mate, he says, no. He says, we just use boiling water. Now, boiling water is a process that can be used to seal anodized aluminium. Okay, he's only a small guy and he may be an exception, but what he's done, he's given me a little piece of material here that has been boiling water sealed as opposed to nickel acetate sealed. I'm wondering whether the weak results that we're getting is because the product has not been finished with a nickel acetate. I know that this particular product has been boiling water sealed, so we're going to give it a try with a few settings and see what we can find. So that gives us a shiny white finish. Now, something I've discovered in my hunt for colours is an interesting technique which I'm going to just try on this. Catch it in the light, right? And it's dark, but it's not black. Ah, now we're getting there. I think we found it. And okay, after a little bit of fiddling, I think we found some results that work on this material. There must be other chemicals in the surface of this oxide which are allowing it to turn black, because this is quite a decent black mark, and it must be just the thickness or the quality of the anodizing that's caused the other problems, the inconsistencies that we had in the other material. But we'll just test those same settings on the piece of angle that I had, which was a good, nice black mark. We'll just test the same Q code on the piece of aluminium bracket that I had. So there's the time and the parameters for black marking clear anodized aluminium. In some ways we're still not all that close to absolutely finding out what that black mark is. We don't know whether this particular product has got nickel acetate in it. We do know absolutely that this piece of clear anodized material has not got any nickel acetate in it. And so where does the black mark come from on this one? It can only be coming from some sort of alloying element within the aluminium itself. Now, one of the candidates could be manganese. There's always somewhere in the region of about 0.5 to 1% of manganese in aluminium alloy. Now, my basic knowledge of chemistry and metallurgy suggests that the mix of oxygen and manganese is a possibility because we've got the right ingredients on this machine: heat, oxygen in the air, and 0.5 to 1% manganese in the aluminium. Now, although that surface does not feel in any way rough or ablated, we won't really be able to take a close look at that until I get my microscope. So I think we're going to have to leave this as a bit of an unanswered question. I think the only conclusion we can come to is that we found a way of black marking clear anodized aluminium very quickly. And now I'm really going to say goodbye to you, and I'll see you in the next session. Thanks for your time.